Hello everyone, I'm Saishnu Manohar from CSEB section presenting my tech talk on computer organization and architecture subject. The topic I've chosen for my tech talk presentation is data flow architectures and multithreading. Let's begin. Let's start with an introduction to data flow architectures and multithreading. Data flow architectures are type of pattern parallel computing model that emphasizes the movement of data between computational nodes. Multithreading is a technique used to achieve parallelism by dividing a program into multiple threads that can be executed concurrently. Both data flow architectures and multithreading are crucial for optimizing performance in modern computing systems. Here we see a diagram of data flow architectures. Represent the computation of as a graph of essential dependencies. Here we can see a logical processor at each node activated by availability of operands, message or tokens carrying tag of next instruction sent to next processor, a tag compared with others in matching store, matching fires execution. Benefits of data flow architectures. Data flow architectures allows for efficient utilization of resources by executing tasks as soon as their dependencies are satisfied. They can handle massive amounts of data and complex computations by leveraging parallelism. Data flow architectures are inherently scalable and can adapt to changing workload demands. Challenges of data flow architectures. Designing efficient data flow architectures requires careful consideration of data dependencies, and scheduling algorithms. Ensuring data consistency and synchronization across multiple nodes can be challenging. Debugging and troubleshooting data flow architectures can be complex due to the distributed nature of computation. Here you see an application, a CAL application giving an input to actor machine, then action execution intermediate representation. Here a map and library are integrated. Then output is given as C plus chisel, backend sequence C, Ambric, Epiphany, and SIMD architecture. Advantages of multithreading. Multithreading improves responsiveness by allowing a program to perform multiple tasks simultaneously. It can enhance performance by utilizing available processing resources efficiently. Multithreading enables better resource management by allowing for efficient tasks, scheduling, and load balancing. Here in a picture represents the advantage of multithreading in Java. Enhancing efficiency, which is one of the main and most efficient advantages. Sharing memory is the second one, reduces runtime and used in complex applications. As we now studied about the advantages, here we studied about the challenges of multithreading. Managing shared resources and avoiding conflicts between threads can be complex, isn't it? Which requires synchronization mechanisms. Debugging multi-threaded programs can be challenging due to non-deterministic nature of thread execution. Multi-threading can introduce race conditions and deadlocks if not properly handled. Here we see a well-depicted diagram of what is multi-threading. Here a new thread is created, it's new, and start function is run. So it's runnable. If it checks it's runnable or not, then if it's runnable, run function is included, then it starts running. So the output is either waiting or dead. If it's dead, we can say it's an end of execution. If it's waiting, we can next use sleep or wait function to activate it. Now let's see and discuss about types of data flow architectures. First one is the static flow data flow architectures have fixed data dependencies and are determined at compile time. Next is the dynamic data flow architectures. Dynamic data flow architectures allow for runtime scheduling and can adapt changing data dependencies. The third and the final one is hybrid data flow architectures. Hybrid data flow architectures combine static and dynamic approaches to optimize the performance and overall durability of the code. Here we see few of the multi-threading models. Thread level parallelism (TLP) involves dividing a program into multiple threads that can be executed concurrently. Tasks parallelism (TP) focus on dividing a program into independent tasks that can be executed in parallel. Data parallelism (DP) involves dividing data into multiple parts and executing the same operation on each concurrently. Here we see a single threading which involves task 1, task 2, task 3, task 4 in a perpendicular order, which means line by line. Here thread 1 is depicted as core 1. An execution time formula can be defined as I summation I is equal to 1 to 4 because you have 4 tasks here and task of I. And here in the right side, we see thread level parallelism where task 1, task 2, task 3, task 4, 4 tasks are side to side each other. And these thread 1, 1, 2, and 3, and 4 are linked to 4 different cores, which is core 1, core 2, core 3, and core 4. In this, the execution time can be calculated with the formula mass max of task of I. Data flow architectures, multithreading. Here we see the basic and main comparison or the differences between data flow architectures and multithreading. Data flow architectures emphasize the movement of data and task dependencies, as we have seen earlier, while multithreading focuses on parallel execution of tasks. Data flow architecture can optimize performance by executing tasks as soon as data dependencies are satisfied, while multithreading optimizes performance by utilizing available resources efficiently. Both data flow architectures and multithreading can be used together to achieve high performance computing, which is very true. Here are some examples of data flow architectures. Khan process network model is a data flow architecture commonly used in digital signal processing and multimedia applications. Synchronous data flow (SDF) model is widely used for modeling and analyzing real-time systems. Actor model is a data flow architecture that represents computation as a collection of independent actors. Here we see a quick diagram and a short diagram which represents a few of the examples of data flow architectures. Here we can see a client side where client requests to the web server in I mean we all search in web, right? So if a client search or requests some gives some input to the web directly gives the information to the database server through a database query. The database server then processes the information and gives a page generator through query results. This page generator again gives back the output to the web server through HTML files. These HTML files from the web server goes to a client side and gets the desired output. This is how the data flow architectures are working. And some of the main examples include Khan process, synchronous data flow, and actor model. These three examples are the main and busy using data flow architectures in present world. Examples of multithreading in programming languages. For example, in Java provides a built-in support for multithreading through a java.util.concurrent package. C++ supports multithreading through libraries such as std-thread and std as async. Python offers multithreading capabilities through threading module. Here is a well depicted diagram in multithreading in Java. Here is a main thread, a method in module where three programs are started: thread A, thread B, and thread C, and each other are put in a switch. So they're switching each other at different times through A, B, and C. Performance considerations in data flow architectures. Balancing data dependencies and parallelism is crucial for optimizing performance in data flow architectures. Efficient task scheduling algorithms can minimize idle time and maximize resource utilization. Careful data partitioning and distribution strategies can minimize communication overhead. Performance considerations in multithreading. Load balancing is important to distribute work evenly across threads and avoid underutilization or overutilization of resources. Thread synchronization of mechanisms such as locks and barriers should be carefully designed to minimize overhead. Granularity of tasks and data partitioning can impact performance in multithreaded programs. Tools and frameworks of data flow architectures. NIFI is a data flow architecture, data flow tool for building data pipelines and orchestrating data movement across various systems. TensorFlow is a popular deep learning framework that provides a data flow programming model for building neural networks. Apache Beam is a unified program model that allows for implementation of batch and stream processing data flow pipelines. Tools and libraries for multithreading. OpenMP is an API for shared memory multiprocessing that supports the multithreading C, C++, and Fortran programs. Pthreads in POSIX standard library for multithreading in C and C++ programs. .NET Framework provides a task parallel library (TPL) for multithreading in C hash and C hash programs. Real world applications of data flow architectures. Big data processing platforms such as Apache Spark and Hadoop leverage data flow architectures of distributed data processing. Streaming data processing networks like Apache Flink, and Apache Kafka use data flow architectures for real time analytics. High performance computing (HPC) applications such as weather simulations, computational fluid dynamics benefit from data flow architectures. Real world applications of multithreading. Web servers use multithreading to handle multiple client requests concurrently. Video game engines utilize multithreading to handle rendering physics simulations and AI computations simultaneously. Database systems employ multithreading to handle concurrent database queries and transactions. Future trends in data flow architectures. The adoption of data flow architectures is expected to increase with rise of big data and distributed computing. Hardware accelerators such as GPUs and FPGAs are being integrated into data flow architectures for improved performance. The research is ongoing to develop more efficient scheduling algorithms and programming models for data flow architectures. Here we see a diagram where a new state is formed through application state, a new state, and subscribers. Action is done, and action is continued to current state, then to the reducer. This is a non-stop process going through in unidirectional data flow in Swift. Future trends in multithreading. The increasing complexity of computing systems is driving the demand for more advanced multithreading techniques. The emergence of heterogeneous architectures combining CPUs and accelerators requires efficient exploitation of multithreading. Research is focused on developing programming languages and tools that simplify multi-threaded programming and ensure correctness. Advantages of multi-threading in Java allows multiple performance at once, save times for execution of multiple operations. Threads are independent at each other. Now we have come to the end of the PPT. Let's discuss the conclusion. Whatever we have learned in PPT, just roughly go through it. Data flow architectures and multi-threading are essential for achieving high performance and parallelism in modern computing systems. Both approaches have advantages and challenges that need to be carefully considered in system design. Continued research and advancements in data flow architectures and multi-threading will shape the future of computing. Here are some references I've used for creating my presentation. Data flow and reactive programming systems, a practical guide by Mark Buzet. Data flow architecture by Behruz Parhami. Multithreading for visual effects by Martin Watt. The art of multiprocessor programming by Maurice Herhili and Nir Shavit. Programming principles and practice using C++ by Jarny Shustrup. Here are some basic questions which can be addressed. Does data flow architecture require special hardware? Yes, data flow architecture often benefits from specialized hardware designed to efficiently handle parallel processing and dynamic data driven execution, but it can also be implemented on conventional processor with varying degrees of optimization. Second question, the most common second question is, how does multithreading impact power consumption in mobile devices? Yes, data flow architecture. So in this parallel processing, the dynamic data execution, but it can be implemented in conventional processor by varying degrees of optimization. Are there any limitations or trade-offs of consider when using data flow architectures? Data flow architecture can face challenges in handling complex control flows and may require careful synchronization, potentially leading to increased design complexity. While highly parallel, they may face efficiency trade-offs in certain sequential tasks compared to other traditional architectures. Thank you. We have come to the end of the presentation. Hope you enjoyed and understood my presentation. Thank you for a valuable time. Have a great day.